Hello, this is Dr. Liu, and we're discussing constant acceleration motion. This is a second video of this. So we have the University of Physics published by OpenStax, Chapter 3, Problem 49. We have slightly modified this problem to fit our needs. So this is slightly different. Alright, so let's go through it. At time equal to 0 seconds, our particle is moving from left to right with a speed of 5.0 meters per second. At the time equal to 10 seconds, the particle is moving right to left while it has reverses direction with a speed of 8.0 meters per second. Assuming the particle's acceleration is constant, determine A, its acceleration, B, its final position, and C, the instant when its velocity is 0. Okay, so I have this already written out so that we have the list of parameters, we also have the equations, and we can set our origin at the initial position so that we can choose x0 equal to 0. And from left to right is typically a positive velocity initial, right to left should be a negative velocity final. And we don't really know the final position, neither do we know the acceleration. Okay, so let's go ahead and start solving the problem by looking at the equations. We can start from either one, but I like to start with from the second one because, see, these velocities are already given and time is already given, so we can solve for acceleration. So equation 2. Final velocity is minus 8. Initial velocity is plus 5. Acceleration times seconds, 10 seconds. So subtract 5 on both sides, minus 13. A equals 10a. So a, if you divide 13 by 10, minus 1.3 meters per second squared. Also checking 2 sig figs, and that should be correct. Okay, so now we have the acceleration. We can plug it into the first equation. So equation 1, we have x equals initial x is 0 plus initial velocity is 5 and times time is 10, then plus 1/2 is 0.5, a is minus 1.3, and t squared is 10 squared. Okay, so 0, 50, 50 minus 1.3 times 100, that's 130, half of that is 65, 65. So we have a final position at 10 seconds, minus 15 meters. Okay, so with just the first two parts, A and B, this is pretty much the same as the previous example, although it's a slightly more complicated. But what is the third question asking? The instant when its velocity is 0. So that is asking the time. Basically, you look for a time, not this time, because you know at this time the velocity is not 0, it's minus 8. Right? You're looking for a different point in time when the velocity is 0. I bet that's when the particle switches from going to the right to going to the left, or where it has done its reversing, right? So that's the time we're looking for, and this is I would say a different final time than the 10. So we can still take equation 2, try to solve it. Let's save some space. I have another question coming up. So equation 2, if I just put velocity equal to 0, because I want the velocity to be 0, the initial is 5, and acceleration is minus 1.3 as I solved it already, and I don't know the time, so I'm solving for this time when I know the velocity has to be 0, and then when I know the acceleration has already been solved to be that. So it's 5 minus 1.3, t equals 0. So t is equal to 5 over 1.3. Okay, so let's bring up our calculator, our Python. So 5 over 1.3, we have 3.846 long, And we know we're supposed to keep how many decimal places. I think it's 2 places, right? The 5 is actually 510. The 1.3 was also coming from that, the 510 minus 810. So we're just going to round it here to the nearest 1/10, and that will be 3.8. Okay, so back here, 3.8 seconds. So that's basically a different final condition with a different final velocity being 0. And you can still use the same acceleration because that's the same exact motion and it hasn't changed. Okay, so let's now discuss another problem. I'm just going to move this up. See if I can do this. Just copy and paste because I need a list, so I'll put it here. Alright, so we have a second question. This one is unmodified from the University of Physics, published by OpenStax, Chapter 3, Problem 64. So we have an express train. It passes through a station. Basically, the express train does not stop at the station. It just passes through it. It enters with an initial velocity of 22 meters per second, and it decelerates at a rate of 0.15 meters per second squared. This means it has a negative acceleration. The reason is probably because of safety. It doesn't want to just run through the station at full speed. It wants to slow down as it approaches, although it's not stopping at the station. Alright, so that should be negative. And then the station is 220.0 meters long. We have several questions. A, how fast is it going when the nose leaves the station? Basically, it passes through this much distance with that acceleration negative. What is the final velocity, right? B, how long is the nose of the train in the station? So basically, how long did the train stay in the station? Because, well, trains could be really long, so we'll just call the nose of the train representing the whole train. So how long is that, right? You can say, well, as a passenger sitting on the train, how long did the passenger basically see the station, right? And then C, well, there's a changing condition. If the train is 130, oh, actually, sorry, just given the train's length, 130 meters long, what is the velocity of the end of the train as it leaves? And then D, when does the end of the train leave the station? Okay, so let's get started with at least part A. So let's list the parameters here. So we know that the train has an initial velocity of 22. Okay, 22 meters per second. It has this acceleration negative, so minus 0.15. And let's take a look at these numbers. 3 decimal place, 3 sig figs. This one has 4 sig fig. Probably not useful. Okay, so what else? We have the station's lengths. So we can start with 0 and end with 210. This is where the nose was when it enters the station. This is where the nose was after it exits the station at the end of the station. So the two unknowns are the time duration and also the velocity. Well, the reason I picked this question is because we don't know time, so this allows us to explore how to solve this system of two equations where one of them is a quadratic equation. Alright, so let's list the equations here. We'll try to split our work from on the left side and then go to the right side. So equation 1, 210 equals 0 plus initial velocity 22t, then plus 1/2, there's a negative 0.15 acceleration, t squared. So this is a quadratic equation full-fledged. It has quadratic, linear, and also constant terms. So let's sort it out. So we'll rewrite it as minus 0.075 t squared plus 22t and minus 210 equals 0, because we're subtracting 210 on both sides, so it shows up on the side with more terms as a negative, and there's a negative half of 0.15, right? So this is our equation. We should be able to solve it with our quadratic formula, and why not, right? We have it that's solvable. We should go ahead and solve it. So with the quadratic formula, this is our a, the a term, this is the b term, this is the c term. So we'll solve for t. T is 1 over 2a, 1 over twice this, so it's still a negative 0.15, and minus b, minus 22, then plus minus square root of b squared minus 4ac, so b is 22, square that, minus 4, a is a negative, let's keep that in mind. Okay, there's a negative I didn't express, and then there's another negative. Okay, so the two negatives will just cancel each other. Good thing I didn't change the sign, right? And we'll put all of these under the square root, and then put parentheses over here. Alright, so with a little bit of TV magic, I can recall these answers, but maybe I should just do it this way. I'll pop up my Python calculator because I have everything here. So all I have to do is to recall my function, which is called the quadratic, so you'll be able to solve me the quadratic equation without having to go through all that math. It's already typed in. Okay, so a value and b value and then c value. Okay, so now I have two answers. Okay, so one of them has about 10 seconds, the other is over 280 seconds. So let's write them both down and try to reason through which one to keep. And for the moment, let's keep 3 decimal places because most of our numbers are 3 decimal places. So 9.88, 283. Okay, so these are both in seconds. So which one is correct? Think about this. What makes more sense is an express train. So it's supposed to pass through a station relatively quickly, and if it stays in that station for a duration of this is almost 5 minutes. It wouldn't be an express train passing through a station anymore, right? So this doesn't make sense. But why are we getting this number in the first place? Well, in the first place, we have a quadratic equation, so it's supposed to produce 2 answers anyway. But what is this answer? Well, let's draw a diagram to see what this means. So if this is the left side of the station, and this is the right side of the station, so this is the left side, and this is the right side. So I'll just draw a little box for the train's nose. So the train moves forward, and it's decelerating. It's reached here and spent X amount of time, and I think this time is 9.88 seconds. And what does it do? We didn't really tell the question that the train will stop slowing down, will just keep going at a constant speed now. So that wasn't really expressed in here anyway. So the mathematics just assume that the train will continue to slow down, and eventually at some point further away from the train station, it has reached zero velocity. And assuming that constant acceleration still applies, it applies a velocity negatively, right to the left. The train will start backing up, and basically it just does this. Moves past the station, slows down until it stops, and then it starts to come back, and then at the station's right side. So this takes a much longer time than that, which is just passing through without keep slowing down, stopping, and coming backwards, right? So that is the wrong answer. This is the right answer. So we'll pick this time 9.88 seconds. So we can take it to equation 2. So equation 2 tells us the final velocity v is initial velocity 22 plus at. So a is minus 0.15 and the time is 9.88 seconds. So I have pop this up. So 22 minus 0.15 times 9.88. So we have 20.5. So that's 3 sig figs. 20.5. So 20.5 meters per second. So slightly slower than when it first entered the station. So that answers this question here. How fast is it when its nose leaves the station? And how long is the nose of the train in the station? So that was this answer here. It spent almost 10 seconds in the station. So let's move on to the next two questions. If the train is 130 meters long, what is the velocity of the end of the train as it leaves? Okay, so we just assume that the train is continuously decelerating until at least the end of the train clears the station before it can decide to do anything it wants, pick up the speed or just keep going at that same rate. So this means the train has to travel, the head or the nose of the train has to travel 130 meters beyond the end of the station in order for the end to clear the station. So the final position is at the 210 meters plus 130. So let's partition our space, and we'll do a detailed diagram here. So assuming that this is actually the station's left and right side, and we have the train here. We'll do a blue train. Oops, I don't know what happened over there. Okay, so this is 130 meters long, and when it reaches here, still 130 meters long, right? And then it has to clear the whole station. It has to drive out of the station until the end of the train is at the station. So over here is 130 meters from where the nose of the train is. So this whole thing being 210 meters, so the nose right here travels from 0 to 210 and further to 340, right? So that's the final position. This is x final is equal to 340. So that's difficult to find out, but it's not impossible. So we have a different set of final conditions, right? We have the same exact, well, if we look at this, the x has been swapped out to a new velocity, new quantity. The velocity is still unknown as we keep decelerating, and also the time is still unknown. So we're basically resolving this whole problem with a different x, right? So let's copy this and just paste it here. Oops, looks like it doesn't want to be moved. Okay, so we have this, and we just erase this number and replace it with 340 when the end of the train has cleared the right side of the station. So we're just redoing this on the left side mirroring what we're doing. So 340 equals 0 plus 22t plus 0.5 minus 0.15 t squared. So the equation we have, the quadratic we have, is still minus 0.075 t squared plus 22t minus, instead of 2 times 340. And we can use the same Python to solve. So let's call that up. Now we can type. So minus 0.075 and 22 minus 340. And I bet two different answers. That's the same thing here. This is when the train actually just formally pulls out of the station. This is when it somehow just keeps slowing down, and then stops, and then starts to come backwards. And this is when the end of the train has returned to the right side of the station. Apparently spending less time than the nose has to return to the right side of the station, right? So we can just skip that answer now, and we'll take a 16.4. So t is 16.4 seconds. And to find out when does it leave, so basically that leaves 16.4 seconds after the nose enters. And then what is the velocity of the end of the train? Well, that's the same thing as the velocity of the nose of the train, right? You don't expect them to travel at different speeds. So this can be just plug into equation 2. The equation 2 is velocity is 22 minus 0.15 times 16.4. So we recall our calculator. 22 minus 0.15 times 16.4. So we have 19.5. So 19.5 meters per second speed when the end of the train has pulled out of the station. Thank you.